Hello, good morning. I'm very happy to be here. So the first thing I wanted to say is to thank the organizers. Thank you for inviting me. It's great. Yeah, this island is great. It's my first time in Japan, so everything is very, very cool. I hope you're having a good time too. Okay, so I will talk about quantum cryptography, as you see probably by the names of my lectures, and we will start really from 101. So I will start very introductory. Maybe I'm less of a good storyteller than Arthur was, so I will say maybe a lot of things that you already know, but I will say a different story. So yeah, so that's gonna be the first lecture. In the next lecture, the one after the break, we will get a bit more into proofs. So you're gonna see like security proof and like maybe like we try together step by step to see how you would prove a quantum protocol, and that's the idea. And so the ones that are on Friday, I will go to more advanced, I would say maybe material. So I will talk about protocols beyond quantum key distribution and beyond the usual like quantum communication stuff that maybe some of you know. And in the last lecture, I will also go beyond the usual assumptions. I will tell you that you can do cryptography, quantum cryptography using other assumptions too. So that's roughly the plan. And the other thing is that please do interrupt me in the middle. I like to be interrupted. I don't want to go all the way for like 2 hours or something. And my first lecture might be shorter, so I probably go all of it without a break, and I will probably give you a longer break at the end. This one, and for the next one, maybe we need more time to go over like the process. So. Okay. So I work in Quantum Software Lab in University of Edinburgh. This is us, if you didn't hear about us before. So we are in Scotland, in Edinburgh. It's a very beautiful city. It's a very different beautiful city than here. It looks a bit like you entered Harry Potter world or something. But yeah, so we're a big quantum theory group. Apparently the largest only theory quantum groups in the UK now. I'm one of the faculties, and yeah, so if you like to come for a PhD postdoc, check our website, check our website, and also if you want to come for a visit. I just wanted to say that. So from next month, we will probably have also a visitor program. So in case you were interested to visit us, let me know, or if you know someone there, let us know. So that's us. Just wanted to tell you where I'm coming from. And okay, so that's the plan for today, which I more or less told you. And I think the idea that I want to pass along today is to having this sort of like resource mindset to quantum cryptography. So, you know, like one way to learn quantum cryptography is that here's a protocol, here's the proof, and that's how it works. You know, that's good. That's very good. But the other way that I like to think about it is that quantum cryptography gives you a very different mindset, and it gives you tools that if you understand why that gives you something that is interesting, then maybe you can go playing around with these resources and construct new things on top of that. So this is what I want to at least I try to do. All right. Cool. So the first question that you ask is that why did we need a new kind of cryptography? Well, we have cryptography, was working pretty well. Why did we need a new one? And so the way I like to tell the story is that imagine you wake up one day and then you like open the news and the news says breaking news, cryptography is broken. So we're like finally there that day that we have quantum computers that can actually break crypto systems, right? So when that happens, there are two options. Either you're in a world that there's no cryptography, so there's panic, there's no secure communication whatsoever, and it's gone. Or you're in a world that we actually have alternative ways to secure communication. That's cool, right? So this is This is the world we like to live in. And so why this breaking news can happen, you all know. The reason is this guy. So Peter Shor, he came up with an algorithm, very theoretical one, but nevertheless, it was like, okay, I have an algorithm, I can factor large number very efficiently. So this is something we assumed to be hard before, right? And this was very cool when this came out, and people were excited because it was an algorithm that was very useful. It was doing something real and something that quantum computers could do, classical computers could not do. But the problem was that, yeah, but that's exactly how we build cryptography, right? So modern cryptography or public key cryptography is based on exactly this assumption. We assume this to be hard, and now we know that it's not. At least there is something that if we do that, then we can do it easily. And that's why it happened, right? Okay, so yeah, oops. Okay, so it's funny. This is slide I wanted to remove it yesterday after I saw Arthur's talk, but I was like, nah, I'm gonna keep it just to show you that how cryptographers think the same, even though they don't communicate. So we kind of had the same story in mind. Like, I'm not gonna tell you again the story, and I'm like sure Arthur said the story so much better than I will do. So it's just to show you that, yeah, so the cryptography is always like, it has been always this like battle between code makers and code breakers. So you make something, you like make it smart, and then there's someone else comes and like, yeah, here's a smarter way to break this. And so it goes and it goes, and it has been the case always. And it was kind of like here that we were kind of sure that we have a very good cryptography. So we were like very confident that cryptography works pretty well. And there was this idea of public key cryptography that Arthur told you yesterday a little bit about, that you don't need to do cryptography in this like weird ways and like share keys that are very long and hard to share. And there's a very nice and smart way that you can, without sharing a key, right, so you have a public key and then you have like your own private key, but without sharing a very big key, you're able to do cryptography. And that was really exciting. And that lasted like what, 24 years before Shor breaks it. But that's 24 years in modern times. So that lasted, I think, quite long. And till like quantum came. And now that the story is that we have now some other cryptography, but there's still the questions that will it hold, will it not hold, and we want to understand what's happening. Okay. Yeah.
What kind of cryptography are communicating?
Yeah, so I was thinking, well, yeah, okay. So the idea was that like the best way you do this is when code breakers and code makers, they work together. So what I wanted to tell you at the end, I think, which I forgot, was that it's very, and I'll come back to this slide and like talk about it more, but it's a very close collaboration between people who break the code and people who make the code that makes a good code and makes a good cryptography. And this is how it works. Okay. So we know Shor's algorithm breaks cryptography because it solves this problem and it does it efficiently. But the question is that when, right? And like, is it already there? So I just put some numbers of the latest numbers of qubits of the best quantum chips that we have today. So this is Google's Willow, this is IBM, the last one is Quantinuum, and these ones, they have like good quality, I would say for now, qubits, but we don't know like exactly how many, like quantum, I don't think anyone knows how many qubits they have. So you might remember from I don't know, like lectures in quantum computing or like introduction lectures or like public talks that you might have heard that, okay, if we have around like 30, 40 qubits, then we're good, right? We're there, we can factor large numbers that already breaks the cryptography. So it looks like we passed that, right? But we didn't, like you didn't hear that breaking news that I had in my first slide, right? So why is that the case? Say it again.
The algorithms and also the processor both are not kind of efficient.
Yeah, especially, yeah, exactly. So the thing is that these are not real qubits. I mean, these are real qubits, but these are not as real qubits as the one you write on the paper. So these are noisy, low quality, and in order to get like one of those good qubits that you write on the paper, you need to pack a lot of these things together and then correct all the errors that can happen on top of them, which is known as error correction. So you need to do a lot of work that out of many of these things you get one good one. So this is in fact not 30 good qubits. And the rough estimates, like at least a couple of years ago, for how many of these qubits I need to get like, you know, enough qubit to break Shor's algorithm was around 1 million. So we're not there, right? That's the idea. But so the question is that, okay, when we're there, because so I told you a couple of years ago that was the rough estimate. Why this has changed? Because the past 3 years, there's been a lot of progress in both hardware and in error correction. So people have come up with better and better algorithms for error correction. So let's say, for instance, before you had to pack, I don't know, thousands of these qubits to get one good qubit. Now you can do it with a couple of hundred or something like that. So this has made a lot of change, and it changes how fast, or you know, when we get those algorithms that can actually break, you know, enough qubits so that we can run Shor's algorithm on top of that efficiently, right? So when current cryptographic protocols become vulnerable to quantum attack is actually not a super straightforward question. It's not like you write your Shor's algorithm and you write the large number that breaks your current cryptography and you say, well, that's it. It depends on the hardware, it depends on what kind of factoring algorithm you use, it depends on how you break your algorithms to smaller parts and run it on the hardware. So it depends on a lot of things. If you're interested, so one thing I wanted to show is that there is this open source library that my colleagues in Edinburgh they developed. It's called Quantum Threat Tracker, and it's the idea is to answer this question that, you know, when our cryptography will be broken. And so basically you can go and play around with it. You can go and change the factoring algorithm. So for instance, there's more than one factoring algorithm, just like other algorithms, I'm sure. And you can also go and change your error correction. You can maybe, like, you know, the newest error correction, whatever, and then play around with these things, and it will give you resource estimation in the sense of, okay, how much resource you would need, and that will give you an estimate on, like, are we still there or not there. And it's getting closer and closer, so it would be fun. So you can scan and go, like, maybe in the break, have a look at it and see how it is. So this is questions? Okay, cool. All right. So we know that this is coming closer and closer, and that if we go back to the question that I asked in the beginning, that why do we need a new kind of cryptography? Because this is going to be broken, the one that we have, maybe even if it's not broken now, it's going to be broken at some point in time. And we need to find new ways to secure our communication. And there's 3 steps that we need to address, and it's like all of them are quite hard. The first thing is that, okay, so this is a problem we need to solve theoretically, and everything that I will talk about today and tomorrow, today and Friday, are on this theoretical regime. So I'm like, I live here. So I'm trying to solve this problem, more or less, right? So sometimes I look here, but like I'm mostly here. But then even if you solve the problem theoretically, if you remember, there was this discussion yesterday in Arthur's lectures as well, that cryptographers, a lot of them, they're pragmatic people. They're like, okay, so I don't care if you can do this, like, you know, on the paper. I want to know that practically how you do it, right? How can I write codes and like implement it? So cryptography needs to be deployable and it needs to be efficient. And this is something we need to work on. And even after we do that, because cryptography is a tool that's widely used, it's not like you wake up tomorrow and it's like, okay, here's your new algorithm, go and have fun with it. No, it needs to change a lot of things because you need to change infrastructure, right? So you need to change, you know, all your protocols or your infrastructures. If you're using things that needs quantum communication, then you need tools to, you know, do quantum communication with. So there's a lot of things that need to be changed, infrastructure and all that things. And what it means is that it will take a lot of time. So if you want to make the system secure before they actually break, you need to do it faster. And so this is something that's like agencies, the standard agencies, the companies, and governments, they realize, and they're looking for solutions. So what is these solutions? There are usually two ways that we know how we can do this at the moment. Yeah, so the first one is that we find new assumptions, right? So like I told you, we assume that, we were assuming that factoring is hard. Well, it wasn't, now it's broken. So we need new assumptions, like new mathematical problems that are hard to solve even for quantum computers. This will be the building block of what people call post-quantum cryptography. This is, as Arthur was saying yesterday, classical cryptography based on new hardness assumption that, you know, will last against the quantum computers. And the other way, the way I like to call it is that, you know, nature broke the cryptography, nature fixed it too, right? So we use the same thing that broke the cryptography to make it secure, which is this idea of using quantum communication. So we will talk about this. I will not talk about post-quantum stuff that much. So we will mostly remain here, but I will talk about assumptions. Maybe different ones, but I will talk about that. And so you will see the Tom and Jerry picture again. The last thing I want to say is that it's not really an intersection that you need to make a binary choice between this or that. A lot of people, me included in the field, think that probably some of the best solutions you can find is when you combine these things. So you use the things that are good in quantum communication, you use the things that are good in computational security or post-quantum stuff, and you make practical protocols. So this is also something that maybe in the last lectures in Friday I will talk about more. Okay. So yeah, so again, quantum cryptography is this idea that we use the power of the nature to unlock cryptography, blah, blah, blah. I talked about those. And again, what I wanted to say is that it's a very, very close relationship between things that break and things that make the cryptography secure. And it's in finding this balance that we find like sweet spot to do cryptography with. So to understand that, because when there's going to be quantum technology, good guys will use it and bad guy will use it. We need to try to understand what are those properties that are interesting, both for the good guys and for the bad guys. Here is again to give you like some perspective and landscape of what this quantum cybersecurity, some people call it, or quantum cryptography is. When you move to the quantum regime, your adversaries are quantum, right? And because cryptographers are very paranoid, Usually you like to assume the worst possible scenario, and you want to make things secure in that scenario. So when we move, we assume that adversaries are fully quantum. But now the honest parties, the parties who run the protocols, you have a couple of options. And the first one is if these are classical, and then you will be in this regime of post-quantum security, right? So when your schemes are classical, but your adversaries is quantum, then you're here, and well, you need new proof techniques, you need new hard problem security definition, and all these things. And then you can have quantum parties. Basically, these guys will run something in between them that is quantum, and here we're in the regime of quantum security or quantum enhanced, as it's being called in this review. And then you can even go one step further, and you can think of a point in time where a lot of things are run on quantum computers. So you have quantum networks, and this quantum network, they consist of nodes, and these nodes are actually quantum computers. So you're in a regime where you have quantum infrastructure and you have classical infrastructure, and they can like work together, and you want to have security here. Now, the thing is that when you move to quantum, it's not just the adversaries and the power that change. A lot of other things will change too. So some of the things are, for instance, definition. When you want to make a scheme secure against a quantum adversary, sometimes you need to change your definition, because the definition that you already have, with which you will prove the security, because it's like a formal step-by-step thing, and does not capture the full power of the adversary or the full power of yourself as an honest party. So a lot of times when you're doing the proof, you need to change the definition. Then you need to change your primitive. These are simple building blocks or protocols or things which you build cryptography on top of that. So this will be changed too. Of course, you change the protocol, this you already know. Yeah, and then you need new algorithms to understand what a quantum adversary can do. Okay, so this was that. Now we'll get to more like technical stuff. Again, I will start very easy, so I hope that I will not bore you, but we'll try to move fast. So let's look at all these properties. So I told you a lot about there's going to be like some properties that are interesting, and I'll try to go over them, and we'll talk together about them. Before I do that, do you have any questions? Is there anything you want to chat about the stuff I said? Okay, good. Let's move on. Okay, so what properties do we have? The first thing that we have in quantum, as you know better than me, are superposition and measurement. So superposition, as Arthur explained very, very beautifully in the first lecture on Monday, or amplitude, is this property of quantum state. It changes the rules of probability, if you want. And yeah, it's one of the most important things you have in a quantum. And then you have the measurement, which is also important because it's a probabilistic process, and it's destructive in the sense that, you know, you can think of it as like, you know, opening an envelope. You cannot just like put it back. When you do a projective measurement, for instance, if you have an unknown quantum state, when you measure its properties in the z direction or in the x direction, you actually like make it collapse. You project it into like this axis or that axis. So it has its properties. So you know about that. I'm not going to longer here. But so is this good for cryptography or bad for cryptography? Well, the answer is both, right? Why is that? So superposition is very important for any quantum algorithm that we know. Like almost all the quantum algorithms, it's not enough to have quantum speed up, but it's one of the most important things that we need. So any algorithm that we build, we usually start with put everything in superposition, or like it uses a state that has some sort of superposition. So in that sense, because it's good for algorithms, it's bad for cryptography because it makes things easy, right? What about the measurement? So measurement, it's really cool because measurement, it disturbs the state of a quantum state, or it destroys it. In some sense, this is good. Why it is good? Exactly. So because it can detect. So if you remember, Arthur was talking yesterday about, you know, like if you do something to the key or like you extract some amount of information, usually classically there's no way you can know. Like I don't know what you have done, I don't know how much of the key you have or something like that. But measurement is the reason that fundamentally is the reason that in quantum we can, because it leaves a trace, right? It leaves yeah, so you can detect it. So in some sense it's good, but it's also bad because you need to adjust it inside your protocols, because a lot of time a protocol consists of being able to check something, and being able to check something always includes measurement. And when you have measurement, you need to know like when you can check something. And so this like balance between the two that makes designing protocols hard, usually. But now, if you put superposition and measurement together, you get a concept called conjugate bases or conjugate coding, and this is super good for cryptography. And we'll see how. Okay, I also prepared a lot of like, you know, like stories to tell you that how cool this guy is, Stephen Wisner, who came up with the conjugate coding. But again, Arthur already told those stories, so I'm not gonna be a storyteller here. But I want to tell you about conjugate basis, conjugate. It's super easy, and I'm sure you already know. But I want to give you this perspective of why I think it's quite cool. So this is Blockosphere. You probably so how many people know, like, have seen Blockosphere before? Everyone has seen. Okay, perfect. So Blockosphere. I don't need to explain this. Blah blah blah. So these are, you know, X, Y, blah 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 bases. But so the idea is that, okay, so conjugate bases, or like encoding in conjugate bases, what it gives you is something very, very cool, because it uses superposition and measurement in the best possible way. So if you have a state, which is in X spaces, let's say it's plus, and you measure in X, of course you get, you know, you get plus, right? So you get it with probability 1. If you measure it in Z, you know that you get it with probability half, you get 0 or 1. But so what is this? What this is that if you encode in a basis and then you measure in the same basis, your process is deterministic. But if you encode in like one of the spaces and you decode in the other one, what you get is uniform randomness, right? Because it's like it gives you uniformly with probability half and half the other two. So in one way it gives you something deterministic, and in one way it gives you something really random. And this is exactly the key that we need. So if you remember, I told you that we need to check a stuff, and we need to also not let the adversary to understand the stuff. And this is exactly the idea that made this possible. And I think it's brilliant. So we will, when we will do QKD, we will just come back to that, and you'll see that it's exactly because of this that things are so nice and easy in QKD. Okay, next one. The next property that's really important in quantum information, and we will use it a lot, is no cloning. So no cloning is that you cannot, usually the way you hear it is like, okay, quantum information cannot be copied. The more precise statement is that if you have an unknown quantum state, you cannot make perfect copies. So this word of perfect and unknown are quite important here. You'll see in a second why. So again, is this good for us or bad for us? This is very good for us. So no cloning is one of the probably most important properties of quantum information in cryptography. It's a lot of security proofs directly reduce to no cloning. If they don't, indirectly they're somehow related to no cloning. So it's kind of like one of the building blocks that we have. The only thing that, like, I can say maybe it's a little bit bad is that because of no cloning, sometimes doing cryptography in a quantum world is harder. For instance, cryptographers, they have these things that is like very useful in classical cryptography called transcript. So the notion of transcript is that when you have a protocol, you have two parties, let's say me and you, we talk to each other, and like I send you a message, you send something back. So the protocol continues with a lot of steps between us. Now, if I record everything that has ever happened, that's a transcript. And if I can analyze that transcript, I know anything that happened during the protocol. And this is usually like super useful for doing proof systems. But in quantum, you don't really exactly have the notion of transcript, because if at any point of the interaction between us, I measure something, then something is lost. Like I cannot keep track of everything that happens. And also, I can, if we send back and forth some states and things like that, I cannot like have copies of that transcript because that includes the state. So I cannot make perfect copies and analyze it and assume that this guy has one transcript, this guy has another transcript. So that makes things a bit hard. And it also makes the notion of oracle, which I will talk about a bit later, hard in the sense that it makes it hard to keep track of things that has happened. Okay, so this is something about no cloning that you find in any textbook. But here I want to tell you something that you don't find in any textbook. And it's this idea that cloning or no cloning and learnability, they are somehow deeply connected. And I will tell you about this because I was really obsessed with this when I was doing my PhD. I was so obsessed with this that I wrote this in my thesis, but it was not something really you could publish. You were like, okay, here's a cool thing. But yeah, so, but I think it's an interesting idea. I want to tell you about it. Okay, so if we go back to the exact, statement of no cloning, as I said, is that if you have a completely unknown quantum state, there's no map that gives you two perfect copies, meaning that there is no unitary that maps this state, or let's say like a blank state if you put next to it, to two perfect copies of that state, right? But if you have the classical description of the state, which I show here as Seaside, then you can prepare two copies. You can prepare as many copies as you want. Like nothing prevents you to do that. It's preparation. This map is allowed, right? So this is not in contrast with no cloning. But the interesting thing is that between these two extremes, there's a lot of other things. And this is, for instance, if I give up on having perfect clones, then quantum mechanics allows me to do cloning. Right, so I can do approximate cloning. So I can start with something completely unknown, but give you approximate clone, meaning that these are states that are somehow close to my state. Okay, so this is allowed. And now the more interesting thing is that if I give you more information, so if I don't tell you that this is a completely unknown state, but if I tell you that, for instance, this is this set of states coming from this set of states, then you can show that you can do this with better quality. And if I like do this, I give it like, if I restrict this even more, if I give you more information about this, then you can do it with a better quality. So the quality actually like increases when you do that. So this is called approximate cloning. This whole field and all these things that happens here is called approximate cloning. It's like a subfield that's quite cool. But the thing is that there is a nice relationship, and you can find it in these two papers by Dagmar Bruce, and one of them is Arthur, of course. every paper you find around that time. So there is a relation between approximate cloning, so this process of starting from some state that you don't know nothing about, or you know some things about, and get something that is somehow close to your state. And the problem of state estimation, or I can call it in some sense with, with a bit of grain of salt, a state tomography. So a state tomography or a state estimation or tomography is this problem or this task that you have an unknown quantum state. So someone gives you a system, it has a state, and you want to know the classical description. You want to know what the state is actually, right? And these two are kind of like linked. And what do we learn from this link and from all these things that I showed you here? What we learn is that, okay, so there is a relation between how well you can clone and how well you can learn. Where does the learning come from? The learning comes from the fact that tomography is a notion of learning. So I also work a lot on learning theory, and I can tell you that this is a learning problem. You can formally define tomography as a learning problem. What is a learning problem? So the learning problem consists of some components, and you put them together, and then you can define like a learning task. So here, the learning task, the first part of a learning problem is data. So you need data, samples, to learn from. What is the data here? The data is quantum state. So you give me multiple copies of a quantum state. Your data is quantum, but that's fine, right? So this is your data. Then the other part of a learning problem is what do you want to learn? The object, right? So the object here is this classical description. And then you, of course, have some measure to know how good or how bad you have learned, which is, it tells you like the quality of this. So tomography here is a learning problem that tells you, okay, how many copies you need to be able to learn a good classical description. And it's related, and we know that in quantum you need a lot of copies to be able to learn a good classical description. And this is related to the fact that you cannot learn quantum state, and the less you know about the quantum state, the less of a good quality you can get when you clone. And I think this is really deep and cool. Now, if you extend this, it gets even more interesting. Yes.
Is there like a bound and that can study that if the description is say 90% of the states inside, this is the maximum we can recover. That's how we're going to work. Is there something like that?
I'm not sure I heard your question completely.
If you have the description cat side and the quantum state is like 90% accurate and describe this state, right?
Yeah.
That's you can do like a lot of these copies. Is there a bound, upper bound that you can say about like how much you can cover about state cat side?
Yeah. Okay. Yeah. So there's
maybe can you repeat your question for the other?
The question is that if we have a state cat psi and you have a constant state of it, say it describes the state about like 90% accuracy, how much can we recover from this? Is that an upper bound to it?
Yeah, so I mean the way I rephrase your question is that if you give me like a measure and you give me like a desired accuracy, let's say, so you want to say like I want to learn a classical description which is epsilon close to my actual description, then one can do the analysis and tell you how many copies you would need to do that. And so we know that for like close enough accuracies, we need exponential copies for tomography. This is a very known popular result. And the same like trade-off also happens in tomography. The same trade-off I was showing you here, that if your state doesn't belong to a set of all states in your Hilbert space, if you restrict the set, then there are efficient algorithms. So then there are ways that with like efficient number of copies you would be able to learn this. So you'll see something similar to that. What makes this connection even more clear between the learning and cloning is when you move from states to processes. This is probably something you haven't seen because you usually know no cloning for states, but actually no cloning also does exist for quantum processes. And for the first time, it's been done by in this paper by Tiribella et al. And the way they define it is that they say, okay, so if you have two black box, O1 and O2, these are like, let's say, black box channels, right? Then the theorem says that you cannot perfectly copy these two on a single use. There are two words here that are quite important. The first one is the black box, and the second one is single use. So black box means that it's a like roughly known concept. You know that like I give you something, you don't see what's inside it, and then you need to interact with it. But you can formalize this a little bit more. And the way I like to formalize the notion of black box is that if I so you have, let's say, a random state, and then I give you two options, right? So you don't know which of the scenario is happening, but either I'm giving you a unitary, which is from your set, so it's, let's say, one of these two, or I give you a completely random unitary. And then with data state, you interact with it, and if you don't know, if you cannot distinguish which scenario you are, then you know nothing about the unitary. And this is one way to formalize the notion of black box. And this is a very useful notion. So I call this a unknown unitary as well. So unknown, like exactly with that. Like for instance, one thing that is not a black box, just to give you a perspective, is that if I draw the circuit of this unitary on the board, right? Then like it doesn't matter. Even if you haven't queried it, you know that this unitary is not a completely random unitary. Maybe you look at it, it's like, oh yeah, I know what this unitary is, right? So that's not a black box. It doesn't matter. Like the notion of black box doesn't right away talk about how easy or complicated the circuit is. It talks about that you have a prior knowledge about that before you interact with it, and this says that no. So this is a black box. And the other thing is the single use, right? So what if I try to extend this definition to multiple use? What happens? Like what does unclonability mean there? So first of all, what does multiple use mean? It means that I allow you to query this black box. So I allow you to interact with this unitary, input a bunch of quantum state, and get a bunch of quantum output. And in this scenario, what cloning means is that if I now give you a new state, let's say sample from a distribution, if you can clone, means that you can give me the outcome of the same channel. So like you give me something that's like close to what my actual channel would have given me. Or I give you some inputs that is somehow related to this like input state, and you're able to give me a function that's like somehow related to the output. But so now this is perfectly a learning problem, right? Because here's your data, here's your target objects, you have your basically distance, favorite distance that you can pick depending on what objects you pick here, and cloning exactly here means how well you can learn this unitary, right? Because if I can learn it, it means that I interacted with this data and I'm able to give you this answer. And this is a unitary learning problem. But it's exactly the cloning problem as well. So the message here is that the extended notion of unclonability from state processes is defined or is linked to the notion of learnability. So Feynman has a quote that I really like, is that what I cannot create, I do not understand. I have a version of I copied a version of the version of this code for this like cloning, and I think what nature says is that what I cannot learn, I do not clone, and this is I think what's happening. And so why this is interesting, because I told you that no cloning is very important for cryptography and you can do a lot of cool things with it. Now you can use another very powerful tool, which is learning theory. And by using learning theory, now you can also do a lot of cryptanalysis, understand a lot of things about protocols and stuff like that. And learning theory, just to recap, I said it I think now a bunch of times, but it's this idea of how I can formalize a learning problem and then tell you how hard or how easy it is. And by hard or easy, meaning that, for instance, how much computation it needs, and more importantly, how much data. So this is a lot about the data. So you have an algorithm, the algorithm interacts with the data, or you give it a bunch of data, and it outputs an object, right? And so usually in computer science, this notion of data, if you want to formalize it and then capture some sort of structure or things like that, you can talk about it with the concept of oracle. How many people know what's an oracle? Okay, no, not so many. So it's good. I can tell you about oracle. So what is oracle? Oracle is this abstract concept in computer science that it's almost like a god. So that's the idea. So you ask oracle question, it gives you answer. That's how it goes, right? So if you have watched the Guardian's Guide to Galaxies, you ask what is the answer to universe and blah blah blah, and it gives you 42. And this is an oracle. That's how it goes. Usually you don't know what's how it does it. You don't need to know how it does it. You just need to know that you have a guarantee that it answers you. But then you can define different oracles. So for instance, I can say, okay, I want an oracle that I have a function, let's say f of x, and I want an oracle of this function. What it means is that I want a box, that this box somehow implements this function. Well, I don't know how it does it, I don't care. But I want a box that whenever I answer some x, it will give me, let's say x star is my queried x, it will give me f of x. So whenever I answer it about f of x, it will give me that, right? So this is as simple as possible oracle. And you can have more and more complicated oracles. So you can, like, for instance, have oracles that implements a bunch of functions together and give you answer. You can have oracles that sample something for you and give you the answer. But roughly speaking, this is an oracle. And so why you describe data with an oracle? Because it's a nice formal way to describe your access model, right? So for instance, your data can be of the form of, let's say, x f of x's, which you can define with this oracle, or your data could be of the form, like the second one that I told you, that you ask oracle, give me something. Maybe you're not allowed to ask, what x you want. And what this does is that it samples an x from a distribution and it gives you f of x for that sampled x, right? So this is a different data, right? So the nature of this data and this data are very different. Like one of them you have like the choice of picking your samples and the other one you don't, and like there's different power in like these two data sets. And this you can capture with a notion of oracle. So this is very useful. Like learning theorists, they use the oracle to deal with this kind of things. And interestingly enough, cryptographers and computer scientists and other things also use a lot this concept of oracle. So okay, so that's that. So you have the relationship, you understand the relationship between oracle or data and algorithm, and then you have your target objects, which is what the algorithm spits out. And when do we say this is learned? When this matches, with some distance measure, or if you do like machine learning, what machine learning people do is they do exactly the same thing, except that they use an empirical distance, because they compare this to not with an exact distance, but with an empirical measure. And when this two matches with the good distance, you say, okay, this is learned, and you need this to be able to evaluate what your algorithm spits out. And yeah, so that's that. So now when you put all these parts together and you study a problem with respect to what is it that you learn, how will you learn it, and what is your access model, this defines a learning problem. And and the take-home message is that, so different flavors of unclonability, you can define it with different like learning models because of this like nice thing. So keep that in mind. On Friday, the last lecture, I will come back to this point and you will be very happy that I told you this before. But yeah, wait for it. Okay, questions? Because I'm going to jump into like completely different stuff. Yes?
I've noticed you mentioned two notions of learning. One is state learning, another is interlearning. So there is some kind of
There's what?
There is some kind of relation between two.
Yeah, so there is, but so usually learning unitaries or like channels, these are you can think of a higher level object that you're learning. So from perspective of learning theory, it doesn't matter that much. You just tell me what is your object, what is the nature of your object, which mathematical space does it live in, and then you can analyze the problem. But in terms of like complexity, usually the more you go up in this hierarchy, the harder the problem gets. So for instance, learning unitaries are usually harder than learning quantum state, which is understandable. One thing I would say that makes the problem of learning unitary learning and states learning very different is exactly in this access model. Because in a state learning, you don't have a lot of options. Usually the most common access model you have is to have copies of a state. So I give you copies of a state row, right? There are different access models, but like the usual one, or let's say the more powerful one, is this. But when I give you a unitary, then there is a lot of options, because I can either give you something similar to that. So I can give you only for a fixed state, I can give you U row, U dagger. So this is, let's say, a state row out. This is the output state. So I can give you m copies of that. So this is one way, but this is very restrictive, right? So this doesn't capture a lot about the unitary. A better one is that if I give you a bunch of different rows, so if I give you row 1 out, then I give you row 2 out, then row m out. So this is better because like it captures more information from the unitary. But you can do even more than that, and you can allow queries, right? So I can allow you to pick your row. So what this makes is that now you can make the next query depending on the outcome of the first query. So you can have like row 1 out, and you can pick your row 2 out in a way that it depends on the outcome of the first one. So this is called adaptive access model. And this is very important because in cryptography, for instance, forget about learning. In cryptography, whenever you have a scheme and your adversary is able to do things adaptively, the adversary is so much more powerful. And there's usually like a lot more power in doing things like that. There's like so much more you can break here than you can break here. And it goes the same thing with the unitary. So now if you think about it from an adversarial point of view, it's really important what kind of access model for unitaries you pick. It's less important for states because you don't have a lot of options, because it gives you this adaptivity property here. Any other questions? Yes.
So, going back to your insight there, two assumptions.
Mm-hmm.
Can you eventually base cryptography? It's a big feature of the fact that some things are redundant.
That's a very good question. Yes, in a way, but I will talk about this on Friday. Yeah. Cool. Okay. So where are we? We're on 1 hour. Okay. So are you happy if I continue, or do you want a break? Okay. So I'll continue. Cool. Okay. So this part I can probably go a bit fast because I think you know. So I'm just gonna recap some quantum information and stuff that is going to be useful, and then I'll come back and talk about more conceptual stuff about these properties that we care about. Okay. So the first important thing is when we talk about quantum states beyond 1 qubit. So larger quantum state, they live in a higher dimensional Hilbert space, in a d-dimensional Hilbert space. But you can also say, okay, I have n qubits, so this is also like a space of quantum objects, and this is a 2n to the n dimensional Hilbert space. The only thing that I think that's important, maybe think about it, is that I don't know how many of you have thought about it this way, but physicists, when we learn about these kind of things, it was like qubit, n qubit, d-level systems, it's all the same to us, we don't care. If you tell this to mathematicians, it was like qubit, n qubit, they was like, wait a minute, how do you do that? Who told you that n qubit is the same object as like the 1 qubit is? So mathematicians, they care about how you compose things. And this turns out to be very important. This is non-trivial. Usually probably the way we learn this is that, okay, here's quantum states, here's a quantum state of 2 qubit. What is this? You just tensor product things. But the fact that you can tensor product things is important. It's not trivial. It's you need to kind of assume it. Then this is not the only way to do composability in quantum, by the way. But this is the way that we think it works. So yeah, the important thing is that composition in quantum comes with tensor product. You can tensor product the bases, and it gives you the bigger states, and the dimension multiplies, and that's it. Nice and sweet.
Where do you think where we cannot do this?
Yeah, that's a very good question. So there are versions of, I found some old papers, so there are versions of quantum in like quantum mechanics in the old foundation paper that they don't assume the composition by tensor product. So usually you kind of like, so some people say that you can derive it, but it's not so true. So usually you need to assume that this is your composition. But as far as I know, there are papers that they show somehow that if you assume some like physically valid structure and some like assumptions and stuff, then you can derive that it has to be tensor product. But if you don't do that, then you can probably have different kinds of compositions as well. Yeah, but I can show you the paper afterwards. I don't remember the name off the top of my head, but I can find it. Okay. Any other questions? So that's just that. So now, what are the most general states? So the two things I want to talk about here in this quantum information part are the most general state and the most general processes. Process and the most general measurement. So these are the two things that we need, because when we move forward and we talk about proofs, we need these things. So okay, so we all know the vector presentation. And we all know, you guys all know, usually like if I do this in a more introductory level, they don't know, but you guys all know that we also have the density matrices, which is another way of like representing quantum state. But I think it's, if you don't know this, I can like quickly say that why did we need the notion of density matrix, right? Does anyone want to tell me why? There's like two reasons that it's like we needed something more than just like bracket notation and vectors.
Well, as an experimentalist, because I cannot be sure that I'm comparing the exact same state all the time.
Yeah, exactly. So this is one of the important ways. What else? There's another reason. Exactly. So there's this two, exactly. So you need to talk about subsystems and you need to talk about ensembles of a state, which is that. So if you have like, let's say this is a state that lives in a composite system, as I was just telling you, in a, you know, like a entangled state or something like that. For instance, if it's a Bella state, if it's a completely entangled state, then you want to be able to talk about the state of the subsystem, right? If you don't have density matrices, you don't have a way to talk about it, because this is not the state up, it's not a state down, it's something else, but it has a system, you know, it has a description. You should be able to talk about this thing. And the other reason is that, yeah, exactly. So for experimentalists, this is important, because when you prepare a state, it's probably a mixture that is sampled from two distributions. For instance, here I have red states and green state, and if I mix them with some percentage, then I need to describe this like state, which is, you know, you can do it with density matrices. So this is the reason that was not enough, and we needed something more general. And this is the something more general. So this is the density matrix, which is an operator. It's a linear operator, and it has all these properties. It's Hermitian, trace one, and positive. And why all this? There's a reason why this property. It's not just because mathematically it's cool. It's because that's the only way that's meaningful for physicists, because if it has all these properties, it gives eigenvalues that are real, positive, and normalized. And that's what we need. This describes an actual system with probability rules for me. Okay. This you don't need. Again, blogosphere. So what I love about blogosphere is that I don't know any other graphical representation in anywhere in the field that's so rich. Like you can just like do a full quantum course from beginning to very advanced stuff just by using blogosphere, and I find this like incredibly cool. So you can talk about like pure state, mixed state, maximally mixed state, which is just like, you know, point in the middle, and everything is here. So you don't really, as long as you're talking about one qubit, you don't need anything else than blogosphere to talk about. So it's kind of cool. And then, yeah, okay, so you need density matrices to talk about subsystem. For instance, if you have a maximally entangled state, the way to talk about this subsystem is that you write its density matrix and you trace out the subsystem that you don't care about. So if I want to know this, I trace subsystem B, and vice versa, and it gives you the description of a subsystem. And so this is also interesting because it gives us, like, once we know this, it gives us a way to talk about entangled and non-entangled state. It separates the two. Because a separable state is something that when I write this description, I can always separate it in a tensor product form between the two states, but you cannot do that for entangled states. And so that's why the density matrix is the Lord of the Ring of states, because it talks about pure state, mixed state, separable, entangled, like everything can be described by this. And the second thing that we need to understand it in the more general form is measurements. So measurement, again, we know projective measurements. You can generalize Born rule and projective measurements with respect to observable. This is like the Born rule. And when you generalize it one step further, what you get is this notion of POVM, positive operator valued measurement. And so yeah, this is the definition. These are positive semi-definite maps. And they need to sum up to identity for the probability rules to make sense. And this is the Born rule. So if you take the trace of your operator on your state, it gives you the probability that you find the outcome that you want. So this is the generalization of that. But you probably know this, so I will not stop here much. Again, so what, this should have, I forgot that. So what you can do with POVM that you cannot do with normal, like with the projective measurement, again, subsystems. So you can like measure parts of your system, which is again very important for experimentalists, because you would want to be able to do that. And you can also describe measurement scenarios that you cannot describe with projective measurement. And I think this is important because this problem is an important problem in quantum information. So what is this problem? So imagine this scenario that I want to go in a lab and do a measurement that when I get outcome 1, I know that it's a state 1. And if I get outcome 2, I know that it's a state 2, but sometimes I get something that I don't know which state it is. So why is this different from the normal projective measurement? Because in projective measurement, usually you go in a lab, you measure, you get a state 1, but you can be right or wrong. So with some probability you're right and you actually have a state 1, or with some probability you're wrong. Here is a scenario which I don't want to have a wrong probability. So I don't want to be wrong, but of course I cannot be right all the time because this is quantum mechanics, so things are probabilistic. So the thing, I push everything to this like third case, which is the probability of ignorance, right? And you can describe this by POVM. So you can write three operators, M1, M2, M3. They should sum up to 1. And the way I define this is, okay, so I somehow mix this projection into the orthogonal state of psi 2 and the orthogonal state of psi 1, and then I construct the last one from that. So this is my three POVM, and this is the only way you can describe the scenario. And what happens is that you can now minimize the probability of I don't know. So you can get the best success probability that quantum mechanics allows you to do this kind of like measurement. And this problem in quantum information is called unambiguous state discrimination, because you don't have any ambiguity. Either you're right or you don't know. And yeah, this is used as building block of a bunch of things, so it's good to know. Okay, so this is the quantum information part, and I will, how much time I have? I will talk a little bit more about a couple of more properties, and then I think we can go for a break. Do you have any question here? Yes.
So is one way to think of a POVM that it like collapses you to a mixed state.
It collapses you to.
It's not like you measure, you get a definite state expansion.
Sure. Yeah. I mean, so you. Yeah. I mean, you can still like apply a projector to a mixed state as well, but yeah, I think I see what you mean. Yeah. Okay. All right. Any other comments, points? Yes.
Sorry. I'm not quite sure what's the expression here. It seems like a projector plus another projector plus another projector. So what does it? What do we call it? POV instead of EDM?
Instead of project, yeah, that's a good point. Because so the projective measurement, so those are projectors or projective operators, right? And their the properties is that they're Hermitian again, and they sum up to 1 and that, right? So here you don't exactly have that, so you need to basically this alpha factor that I'm putting here. You know, it changes the weight. You see, so this is on its own. So okay, so if I don't put the last one, this and this doesn't make a complete set, because then I needed to like remove them, and then they were like a complete set of projectors, like they would form a basis. But I'm kind of like, let's say put a half here or like something else here. So I'm mixing them in a way that this on its own is not a like this and this without the last one is not a projector. And in fact, it's yeah. So it's a different operator. It's like a positive value. Does it make sense or? Okay. I think I didn't explain it very well, but yeah. What else? What else about POV? I didn't talk about the channels, but I actually had a slide on that, but yeah, I removed it. I was like, you guys know CPTP maps, so I don't need to talk about that. Okay, let's move on. So before I show you the last part of the properties, so what did we see? So we talked about cloning, no cloning, all that things, and superposition and measurements and these things. There's one other important properties that we know in quantum, and that's entanglement. But so like I said, okay, here's entanglement, but I want to say like what is the properties of entanglement that it's actually important for us and for cryptography. Okay, so entanglement. So first thing, which Arthur yesterday talked about, is that they capture non-local correlation. So I don't talk about that. The thing that's quite cool and important, I think, is that this non-local, these properties, they also exist in the statistics that you get from the measurement. So if you work in quantum foundation, you're familiar with that, or if you've heard about that you can think of these statistics that come from this sort of correlation, even without assuming quantum mechanics. So you can think about like general theories that are probabilistic and will tell you this sort of thing. And those general probabilistic theories, quantum mechanics is one of them. But what's important is that even if you don't have quantum mechanics, you can have entanglement, and you can have these like fundamental properties of nature that will tell you things that are non-classical. So you can have non-classicality if you have entanglement, even if you don't have quantum mechanics, which might sound like a weird thing to say, but trust me, this is true. Okay, so this is one of the properties. And the other very important properties is that if you have a maximally entangled state, which I wrote, if you look at the state of the subsystem, so you can do this exercise on your own really quickly, and you can see that this is always maximally mixed. So the subsystem of a maximally entangled state is maximally mixed state. Now, maximally mixed state is a very useful state in cryptography, as you will see, because it doesn't contain any information. And why is that? Because if we go back to blockosphere, because it's the center of the blockosphere, it's basically, you can write it as any two pure state, as combination of any two pure state you want. So it can be any of these things. You have no information what the hell this states could have been. So it contains no information, and it's really, really good for cryptography, because if I can work with maximally entangled state in a way that an adversary only always have the local system, then the local system gives no information to the adversary. And that's the main idea we will rely on later. Then, what else I want to say? Yeah, so the other thing that's quite useful, and you will see that, is that these like entanglement or being maximally entangled is basis independent. So I can write it in the 0-1 basis, and it looks exactly the same if I write it in the plus-minus basis or any other complete basis. And this is very useful because I can go from one basis to another, and this like still captures this structure, and it's useful. And the last property is that maximally entangled states, they have this property that is called monogamy of entanglement. What is monogamy of entanglement? What it means is that if you have two systems that are maximally entangled, and if someone tells you that this is, there was actually a third party here as well. So this is actually a part of a tripartite system. Now, what you know for a fact is that this part and this part are tensor product. So if I have maximum correlation here, then I have no correlation here. And it's written as this. So if I have the trace of, so if I have rho AB being maximally entangled, and someone tell you that this is the trace of E, the last subsystem of this state, then you know that E is in the tensor product form. And again, this is a very useful property for security proof. You will see that later. So these are the things that we are interested in about entanglement. And the last thing is about measuring properties of quantum system. So you can measure quantum system itself. So we talked about that, but what it means to measure properties. The first property that is not property of one system, but it's the property of like two systems that are sitting next to each other is their distance. So this is something that a lot of times you would want to know. When you work with the state, you want to know how far or how close they are. And there are many ways to capture distances between states. I tell you the two most important and useful ones. The first one is trace distance. And trace distance has this like mathematical definition. You write it, you work with it. But to give you a bit of intuition, what is trace distance? If you think of quantum states as distributions, then this is what trace distance captures. It captures the distances between two distributions. So it's somehow a generalization of a total variation distance. So you can think of it as like this unknown quantum state that I have that I want to know how far it's from. This one is kind of like, it's as if it's sampled from some distribution. But like just to give you a perspective, it's not that. And it also measures the distinguishability between the states. So you will see that. I'll talk about this. But yeah, so this is one way. So it's half of the trace norm. You can write it as sum over eigenvalues of this operator rho minus sigma. So usually this is the easiest way to calculate it. We will do that on Friday for something. So it's a good idea if you like write down the definition, if you know how to work with trace distance. But yeah, you can do it like that. But usually you write this operator and the sum of the absolute value of the eigenvalues like this. It gives you the trace. The other distance is when you think of quantum states as like vector or matrices, and you look for their overlap. So you can think that this is my state psi, this is my state phi, and if I want to know how close or far they are, I will look I will look at this angle, right, somehow, or I will look at their overlap, like how much overlap they have. And this is captured by the distance, by the fidelity. So infidelity actually is the distance. Fidelity is the notion of closeness. But yeah, so we can not be mathematicians and think it's like that. And so for pure states, it's the square of the overlap between the two states. It's quite easy to calculate. For one pure state and one mixed state is still, you can write it as this sort of like overlap. For two general mixed state is this expression, which is called Ullmann fidelity. So this is a bit like harder to calculate. if you work in this field, in theoretical quantum information, the first thing that you will know is that these two distances, they don't map directly to each other, and this is such a pain. When you do proofs and stuff, sometimes it's a lot easier to work with fidelity or the other way around, but so there's some inequality that relates fidelity and trace distance in their most general form. For pure state, it's easy, but for mixed state, they're bounded by each other. They're not equal to each other all the time. And this is something that makes our lives very hard in general, but yeah, it's important to know, I think. So you will see some trace distances here and there in my slides later. So I wanted to set this right. And the last thing is distinguishability. Is it the last thing? I think it's the last thing. So I talked about trace distance, and I told you that this is a measure of distinguishability. So what is distinguishability? You can define it as a formal problem. You can say that assume I give you a set of states, 1 to n, and then someone, Alice, chooses one state randomly, chooses one state, whatever they want, and they send me the state. And from the state, I need to find the index. So I need to know, I don't need to know exact description of this. I mean, if these are known description, that I will know, but the task is to find which one it is. And so Bob can make any measurement, right? That's the key. So one of the most fundamental theorem in quantum information is that non-orthogonal states, they cannot be perfectly distinguished, right? So if this set contains even only two states, and these are not orthogonal, they're not completely distinguishable. So they're sometimes I will make mistake, and this is inevitable. And yeah, so here I wanted to, so I have the proof of why, the proof of this theorem using POVM, because now we don't want to do it with projective measurement because they're not the most general measurement. We want to do it with POVM. And but I'm not going to do that. So I'm going to flash this slide really quick, and I want you to write in the break or at some point after I finish to do this proof. It's quite easy and cute to do. So you can just try and do it. then we can come back and I show you the proof and how it works. So this is it. That was a proof. But it's very easy. And in general, this fundamental bound of how well you can distinguish general state is known as whole-level bound or whole-level Hellstrom bound. And what it tells you is that it links the probability of distinguishing, the optimal probability of distinguishing states to their trace distance. So here, this is the trace distance that we've seen, and this is the probability. And again, this is the super useful bound. Yes. So it wasn't the last thing. The last thing was entropy. Entropy. What is entropy? So that there's two entropy that I will talk about. The first one is Shannon entropy, or in the classical information. The first thing you learn, the first thing that captures information quite nicely is the notion of entropy. And so entropy you can define for a random variable, x, let's say. The average information of this random variable is captured by entropy. So the entropy is this expression, P log P. If it's a binary, you can write it like that. And so the important thing is the limits of this, right? So when this is 0, when your entropy, when you write this down and this is 0 for your random variable, you have a deterministic random variable, so you have 0 randomness. And in the limits when things are maximally random, this is log n. So this gives you really a nice measure of how random things are. You have the similar thing in quantum, because quantum states, or density matrices specifically, they're sort of random variables, right? So I just told you in 2 slides before or something that you can think of them as distributions, and you can think about their distance as some sort of generalized total variation. So they are some sort of natural random variables. And so von Neumann has defined a similar notion for states. And for state, it's like described like very similarly to the Shannon entropy, with the difference that these PIs, these probabilities, are the eigenvalues of your rho. And again, if this is 0, you have pure state, which means you don't have any uncertainty. You know exactly what your state is. And in the limit of log n, this is maximally mixed state. So it's the least pure state. So here it gives you a measure of randomness of your random variable. And here it gives you a measure of purity or mixedness of your state, which is, also kind of like its randomness. And then you can define different, like similar quantities in classical, and also they have equivalent in quantum. So this one I talked about. The other one that's important, and I will talk about in the next lecture, is this concept of mutual information. So it's the amount of information that you obtain from a random variable. Like it's something between two random variables, and it's a measure of like how much information there is from one to the other. So it's the amount that you obtain from one random variable by observing the other one. And the way you write it is the sum of their Shannon entropies minus their joint entropy. So this gives you the mutual information basically. So we will use this quantity. The only thing that you need to know or think about is the conceptual definition, like what it conceptually means. It really captures this like mutual, it's exactly what it is. It's a mutual information between two random variables. And then you can define conditional entropy, or you can define relative entropy, but I don't really work with these two at the moment, so you can like leave that. And yeah, so everything that I told you about, you will see somehow one way or another in the rest of the lecture, or at least hopefully. So that's it. I think that's the first part of my lecture. Questions? Yes.
Also, much of a question on the role of common elements in MD, which information stuff. Whether you represent the diagram,
Represent what Venn diagram?
Yeah.
Yeah, you can.
I think the last slide that you showed us, it's easier to represent if you show a Venn diagram instead of the formula.
The formula, yeah, no, you're right. Yeah, that's fair. But yeah, it's kind of like you can see that with the Venn diagram. Quite easily, yeah. It's just like some of these minus the difference, so that gives you the mutual information. Yep. Yeah, good point. Thanks.
In which cases would you rather use the von Neumann entropy instead of the purity?
For Neumann entropy as a purity.
Instead of the purity.
Instead of the purity. Whenever you care about like the information that you know about the state, I would say. I mean, you can use it as some sort of like purity measure. So that's that. So it is used for that. But one reason maybe like cryptography uses the entropic notion more is exactly because this captures like the notion of information better, or like how much information one party has as compared to the other one. So maybe that's one reason. Yeah, I think that's. Yes.
Curious question. So, is the goal of having a secure database with this monogamous, so it's monogamous with the structure?
It's monogamous with what, sorry?
So is the goal of like having a secure cryptography is having this monogamous
It's the goal to use the monogamy entanglement. Yes, is that your question? it's not so much of a goal. It's a property that you will end up using somehow. But yeah, it's so you will see that the way I'll do the proofs are slightly different, and you will see why in the next lecture after the break when we'll do that. But the thing is that there are different versions of QKD, as you will see. And these different versions, people have also done very different versions of proofs of them. So they started from, oh, here's the protocol, it works, you know. And then the cryptographers were like, oh, no, that's not a full proof. We need to formalize it better and better and better. So there are some versions of some proofs of some versions of QKD protocols that they have done it through monogamy of entanglement. They were like, okay, you know, it's like it shows that, for instance, if these two guys are entangled, then the adversary couldn't have been entangled maximally with the two. So that's that. The reason that monogamy of entanglement is not the best tool to do the proofs for entangled based QKD ones that I will talk about later is that it's kind of like a existence theorem. So it tells you that, okay, if these two guys are entangled, then the last one is not maximally entangled, but it doesn't tell you how much, right? And when you want to do the proof, you want to quantify like the success probability of the adversary. Usually that's what you're interested in. And that doesn't like directly give you that. Like it's the fundamental reason behind the proof, but it's not like the best tool. And that was a good question. Anything else? Yes.
Thank you for the talk. I was just wondering in this slide, is there like a deeper connection between Shannon's entropy and von Neumann's entropy in the sense that maybe you can go from one side to the other by doing some manipulation, you know, because the probabilities and the eigenvalues are kind of like related in some sense. So I was just wondering if there was this connection between both.
So that's a good question. I think the way I like to think about it is uncertainty, because like entropy in the classical sense, and that's why it's really, because uncertainty and information are kind of like the two opposite sides of the spectrum, right? And so people say, okay, like entropy captures information, but it actually captures the lack, or, you know, like having uncertainty. That's what it captures the most. And in quantum mechanics, you have this uncertainty that's like coming naturally from the fundamental physics, right? It's coming from the postulates of quantum mechanics. And that's why they're like so related. Like you can write one very similar to the other. And well, so one other thing that I can say that is that you can also think of classical random variables as quantum states, and this is also something that is very useful for some proof techniques. So a lot of times you're dealing with a scenario where you have a quantum state and you also have some classical information. And if you want to analyze them separately, it's a bit annoying, but one way you can analyze it, which is usually quite nice, is that you can construct these things that are called quantum classical states. So quantum classical states are exactly this. You think of this like classical part as a quantum state, you put everything under the same umbrella, and this is still an object that you can talk about as entropy, and it's like Shannon entropy, von Neumann entropy. So yeah, you can like work with them at the same time as well, because they're like closely related. But I don't know if I answered your question, because I think it's a deep question. So.
I think you gave a good answer.
Okay.
Thank you.
Okay. You think we can go?